Assalamualaikum and good morning. We are from BRT 41. Today we will present our project on the design and simulation of low pass filter and band pass filter. Our project focus on designing RF filter using theoretical calculation and validating the design through advanced design system ADS simulation. Before we begin, let me introduce our group members. Thanaseelan anak lelaki Balan, Haaran anak lelaki Sukumaran, and Fateha binti Abdullah. Now let's begin our presentation. Our presentation consists of 4 sections: introduction and theory, realization and result, discussion, and lastly is conclusion. Introduction. This project focuses on the design, calculation, and simulation of two important RF filter. A maximally flat low pass filter, also known as butterworth filter. A 3 dB equal ripple band pass filter. These filters are essential in RF and microwave communication system because they remove unwanted signal while allowing the required frequency to pass. For the band pass filter, we use conventional lump components such as inductors and capacitor. For the low pass filter, the lump design was transformed into a distributed microstrip structure using Ricci transformation and Kuroda identities, making it suitable for microwave implementation. Finally, both filters were simulated using ADS software to verify their performance. RF filters help improve signal quality by rejecting unwanted frequency and reducing interference. There are 4 common filter types: low pass filter, high pass filter, band pass filter, and band stop filter. A low pass filter allows frequency below to cut off frequency to pass while attenuating higher frequency. A band pass filter only allows a specific frequency range to pass and blocks frequency outside that range. In this project, the low pass filter was converted into a distributed microstrip, designed for better microwave performance, while the band pass filter use lump, inductors, and capacitor for frequency selective analysis.
So now let's focus on the task that we given. For the task 1, you have to use the low pass filter. The task given was cutoff frequency 3.2 GHz, insertion loss 35 dB at frequency which is 8.2 GHz, and the ripple is maximally flat. So first we need to find the n value. So we have to find the angular frequency. Angular frequency need to divide by angular cutoff frequency, then need to minus with 1. So 8.2 GHz divided by 3.2 GHz, we can get 2.5625. Then need to minus with 1. Then we get 1.5625. Then referring the table at number 3, we can get the value of n, which is 5. So at the picture number 4, we can find the value of G, G1, G2, G3, and G4 and G5 for the n value which is equal to 5. So G1 is 0.618, G2 1.618, G3 2.0, G4 1.618, and G5 is 0.618. So for the next step, we need to find the value of capacitance and inductance. Our prototype circuit is in the slide at top right corner. So we need to find the value of C1, L2, C3, L4, and C5. So we're going to use the G values that we get before. The formula is for the shunt capacitors are the GK value need to divide by impedance and angular cutoff frequency, and for the series inductors we need to use the formula of impedance multiply with GK values and need to divide by angular cutoff frequency. So we done the calculation here. Then we get the value of capacitor C1 0.6146 picofarad, L2 4.023 nano henry, and for C3 1.989 picofarad, and L4 4.023 nano henry, same as L2, and C5 the value is same as C1, which is 0.6146 picofarad. So for the next step, we're going to use apply Richards transform using the G values. So for this we have to use the formula. For G1 we have to use the 1 over 1 by G1, which is 1 over 0.618. We get the value of 1.6180. Then for G2 it will remain the same, 1.618. G3 will be 1 over G, which is 1 over 2. it's also 0.5. For L4 it remain the same, 1.618. For C5 we need to use the formula 1 over G5, which is 1 over 0.618. We get 1.618. So this is our filter design after the Richards transform. So in this slide, we're going to transform the impedance value of our design. As I showed in the slide at top right corner, we're going to split this design to left and right side. For the left side, the TL value will be 1, and for the right side, TL will be also same 1. So there are 4 Ki identities. We're going to use 2 of them, which is for shunt step. The case 1 is shunt step following by TL, and case 2 TL following by shunt step. So for the left side, we're going to use the case 2 TL following by shunt step. So as we can see, the TL value will be Z1, which is 1, and Z2 value will be 1.618, which is for shunt step impedance. So we can get the value of n square by using the formula of 1 plus 1.618 over 1. We can get the value of n square, which is 2.618. Since both left and right values of TL and shunt step values are same, so we can get the new impedance values also. The Z1 values, Z2 values for left and right will be same too. The middle value will be same since we didn't touch them. We only changed the value of the Ki at left and right side only. We can get the Z1 over n square value 0.382 and Z2 over n square equals to 0.618 for both sides. So at the last picture here, we arrange the values we get. So this is our final design. Next, we need to transform another time for the short stubs. The middle one, open stub, no need to touch. We have to split the design to 4 different categories, which is A, B, C, D. So for this transformation, we have to use another 2 Ki identities, which is series step following by TL and TL following by series step. For this one, for A, we have to use the TL following by series step, and for B also same, we have to use the TL following by series step. And for B and C and D, we have to use the series step following by TL. So after we apply the calculation here, we can get the value of A and D will be same, and B and C values are same still because the values here are identical. So for A and D, we can get the value of new impedance of 1.382 for Z1 and Z2 3.618. For C and B, we can get the values of Z1 2.236 and Z2 0.854. So we can arrange them in the design in next slide. Now at the last stage, we can arrange the values we get here. So all the studs will be open circuit. Since we get all the values, we arrange them here at the first picture at the top right. So for the first picture, the normalized impedance for different stubs. So we have to denormalize with 50 ohm impedance for different stubs. At the second picture, at the middle one, we multiply it 50 ohm and we can get the values here. Next one, at the last one, is we have to do the microstep realization. We get the 180.9 ohm at A and D, and B and C we get 42.7, and the middle one 25 ohm. So at the microstrip, the input value will be 50 ohm and the output value will be 50 ohm too, and the 180.9 ohm will be thin, for it's identical with A and D are identical, so they will be thin. And for B and C, 42.7, so it must be thicker than A and D. And the middle one, the 25 ohm, will be much thicker from others. So this is our final output of microstrip realization. Here we have the software verification for our lump element low pass filter. First, we translate our manual calculations into the ADA software. You can see the circuit schematic on the left. We build it using our exact calculated values, which is 4.023 nanohenry inductors for L2 and L4, and our 0.6146 for C1 and C5, and 1.989 picofarad for C3. The graph on the right displays the simulated S parameter frequency response. If you look at the marker M1, it positioned exactly at our 3.2 GHz cutoff frequency. The insertion loss is negative 3.006 decibels. This perfectly aligns with the theoretical 3 dB cutoff point for maximally flat butterworth response. More importantly, mark M2 is placed at 8.2 GHz, and it shows the attenuation of negative 40.857 decibels. This shows our project is success with the project requirement of 35 decibels of suppression, which prove our choice of n equals to 5 filter order was correct. Next, here we got the schematic at the left side. We can see how we translated our electrical design into physical dimensions. We took the final characteristic impedance we calculated earlier and used the ADS line calculator tool to determine the exact physical width and length in millimeters for each copper trace based on our specific board substrate parameters. So we use MLIN components for the connecting transmission lines and MLOC components to represent our shunt open stubs. And also we use MTEE components to accurately model the junction points. Looking at the frequency response graph on the right, the distributed design successfully mimics the LAM version of our target operating range. At the 3.2 GHz cutoff, the insertion loss is accurately at negative 3.5 dB. At our stop band target of 8.2 GHz, the filter achieves a deep attenuation of negative 41.6 decibels. While the graph displays the typical periodic repeating response inherent to transmission line filters at higher frequencies, it strictly meets all of our design constraints. Most importantly, this design is fully optimized for physical PCB manufacturing. Moving on to the physical realization of our low pass filter, this slide presents the final microstrip layout that we generate in ADS. So below the schematic, you can see the actual 2D layout generated by the software. The red areas represent the physical copper traces that will be printed onto the PCB board. As you can see clearly, all the vertical traces are open segregated at one end. This perfectly visualizes why we performed those complex KI identity calculations earlier. It allowed us to convert an unbuildable circuit into easily manufacturable board without needing to drilling.
Okay, now we are moving to the bandpass filter design. In this slide, I would like to introduce the design of the bandpass filter. Unlike the low-pass filter, which allows all the frequencies below the cutoff frequency to pass, a bandpass filter only allows signals within a specific frequency range while rejecting frequencies above and below that range. For this project, the filter design is designed with a center frequency of 3.2 GHz, a bandwidth of 310 MHz, and a 3 dp equal ripple response, and n is given as 4. The equal ripple response, also known as the Chebyshev response, provides a sharper transition between the pass band and stop band compared to the Butterworth response, although it introduces a small ripple within the pass band. The insertion loss method is used throughout the design process. This method enables us to determine the filter order required to certify the design specification and then calculate the cross-bending inductance and capacitance values for each resonant section. In this slide, I would like to explain about the prototype of the bandpass filter. This slide illustrates the design procedure used to obtain the final bandpass filter. The design begins with the normalized low-pass prototype, which provides standard element values for filter synthesis. Starting with the low-pass prototype makes the design process much simpler because it provides a mathematical model that can easily be transformed into the other filter types. Next, frequency transformation equations are applied to convert the low-pass prototype into a bandpass prototype. During this transformation, every prototype element is replaced with a resonant LC circuit consisting of an inductor and a capacitor. Since the required filter order is n equals 4, the final design contains 4 resonant sections connected together. Each resonator contributes to the overall frequency response by shaping the pass band and increasing the attenuation outside the desired frequency range. This transformation ensures that the filter meets the specified center frequency, bandwidth, and frequency selectivity while maintaining the required insertion loss performance. Okay, in next two slides, I would like to explain about the calculation for the bandpass filter. Okay, this slide shows the calculated component values for the final bandpass filter circuit. Using the frequency transformation equation, the inductance and capacitance values for each resonator are calculated based on the normalized prototype values. Each resonant section consists of an inductor and capacitor that work together to resonate at the required operating frequency. The calculated values are carefully selected so that the filter provides the desired center frequency of 3.2 GHz and a bandwidth of 310 MHz. Every resonator contributes to the overall frequency response, allowing signals within the passband to pass with minimum attenuation while rejecting unwanted frequencies outside the passband. These calculations are very important because they directly determine the filter's performance. Once all component values have been verified, the complete circuit is constructed and then simulated using ADS to confirm that the theoretical calculation match the expected frequency response. In this slide, we can see we have been calculated for the inductance and capacitor, which is L1, C1 and L2, C2. Okay, now in this slide we can see the continuation calculation of the previous slide. In this slide we can see we have been calculated for the inductance 3, capacitor 3 and inductance 4 and capacitor 4. Okay, now we are moving to the last slide of the bandpass filter. In this slide, I would like to present the ADS simulation results for the completed bandpass filter. ADS, which is Advanced Design System, is used to simulate the circuit before fabrications so that the filter performance can be evaluated accurately. From the simulation, we can observe that the filter operates at the design center frequency of 3.2 GHz with the required bandwidth of 310 MHz. Within the pass band, the insertion loss is very small, meaning that the desired RF signal can pass through efficiently with minimal power loss. Outside the pass band, the attenuation increases rapidly, showing that unwanted frequencies are effectively rejected. The simulation result closely match the theoretical calculations, confirming that the design process was successful. This also demonstrates the importance of ADS simulation because it allows engineers to optimize circuit performance, identify possible problems earlier, and reduce both development time and manufacturing cost before building the actual hardware. Thank you.
Now I will discuss the performance of the low-pass filter. The lump element low-pass filter was successfully designed using the insertion loss method with a cut-off frequency of 3.2 GHz and a fifth-order butterworth response. The calculated inductance and capacitance values meet the design specification and provide the required stop band attenuation. However, lump element filter became less accurate at microwave frequency due to parasitic inductance, parasitic capacitance, and component tolerance. To overcome this limitation, we apply Ricard transformation and Kuroda's identities to convert the lump components into transmission line stop. The distributed filter offer better impedance matching, lower insertion loss, and improved performance at high frequency, making it suitable for RF satellite and 5G communication system. Next is the discussion of the bandpass filter. The bandpass filter was designed with a center frequency of 3.2 GHz and a bandwidth of 310 MHz using a fourth order equal ripple response. The calculated component will allow the filter to pass only the desired frequency band while rejecting unwanted signal outside the pass band. This improves signal quality and reduces interference in wireless communication system. Overall, the insertion loss method proved to be an effective approach to microwave filter design. In addition, ADS simulation successfully verified the filter performance before fabrication, helping to reduce development time, material use, and manufacturing costs. These filter design techniques are widely used in modern communication systems such as 5G networks, radar, satellite communication, Wi-Fi, and IoT devices. In conclusion, this project successfully designed and analyzed both the low-pass filter and band-pass filter using the insertion loss method. The lump element loss pass filter was transformed into a distributed microstrip implementation using Richard transformation and Chorus identities. ADS simulation confirmed that both filter achieved the required frequency response and performance. This project enhanced our understanding of RF filter design and demonstrate the importance of RF filter in modern wireless communication system.